So let's take a look at surface area. Now surface area is usually written as capital A of S. And so the formula for surface area is going to be equal to the double integral described by the region D of the square root of 1 plus f sub x squared, or in other words the partial derivative of the function with respect to x, plus f sub y squared, or the partial derivative of the function with respect to y squared. And then we have the dA on the outside. Now since most of the functions that will be given to us are in the form z equals some multivariable function f of x, y, then we can also rewrite the formula as the double integral described by region D of the square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared. And then we have the dA obviously on the outside. So for this next set of problems, let's go ahead and find the area of the surface. So for number 1, let's find the surface area of the part of the plane z equals 2 plus 3x plus 4y that lies above the rectangle. And so the x dimensions of the rectangle are 0 by 5, and the y dimensions, or the y bounds, go from 1 to 4. So once again, if I were to rewrite the formula for surface area, it's going to equal the double integral described by the region D of the square root of 1 plus f sub x squared plus f sub y squared. And then we have dA on the outside. Now the region D in this case is just going to be the rectangle, which has the dimensions, or the x dimensions go from 0 to 5, so I can write in an inequality the x bound is from 0 to 5, and in another inequality the y bounds range from 1 to 4. Now the function that is given to us is the plane, the equation of the plane z equals 2x, or 2 plus 3x plus 4y. So if we were to find f sub x, or the partial derivative of the function with respect to x, f sub x is going to be equal to, well, derivative of 2 is 0, derivative of 3x is going to be 3, and then plus the derivative of 4y is also 0. And so f sub y, if we were to find that, the partial derivative of the function with respect to y is just going to be 4. So if I were to plug everything into the formula for surface area and rewrite it, the formula here, we have the double integral. So I'm just going to write inside the square root of 1 plus f sub x is 3, so f sub x squared would be 9, plus 4 squared, which is 16. Now we can go ahead and put the x and y bounds on either the inside integral or the outside, doesn't matter. Let's go ahead and put the x bounds on the inside and the y bounds on the outside. So we go from 0 to 5 on the inside integral. Since those are x bounds, I'll put dx first. And then we go from 1 to 4 for the y bounds, so dy will be on the outside integral. Now if I were to go ahead and simplify this, we'll get the double integral, the outer one from 1 to 4, inner one once again from 0 to 5. Now 1 plus 9 is 10, 10 plus 16 is 26, so we get the square root of 26 dx dy. So now if I were to go ahead and evaluate this, if I write the inside integral from 0 to 5 of just the square root of 26 dx, since square root of 26 is a constant, the integral of the square root of 26 with respect to x is just going to be the square root of 26 times x. So now we can evaluate that from the x bounds of 0 to 5. So when I plug in 5, we'll get the square root of 26 times 5 minus, when I plug in 0 for x, we get 0. So then 5 minus 0 is 5, and 5 times the square root of 26 is what we get. So now we can go ahead and integrate the outside from 1 to 4 with respect to y this time. So since 5 times the square root of 26 is a constant, the integral is just 5 times the square root of 26 times y. Let's go ahead and evaluate that from the y bounds of 1 to 4. So when I go ahead and plug in 4 for y, we'll get 5 times the square root of 26 times 4 minus, when I plug in 1 for y, we just get 1. 4 minus 1 is 3, 3 times 5 is 15. So the final answer for the surface area is going to be 15 times the square root of 26. So now for number 2, let's go ahead and find the part of the cylinder, or the surface area for the part of the cylinder y squared plus z squared equals 9 that lies above the rectangle with vertices 0, 0, 4, 0, 0, 2, and 4, 2. Now notice that our given function is going to be the equation of the cylinder, y squared plus z squared equals 9. So if I go ahead and rewrite that. Now in the previous problem, the function given to us was in the form z equals something. So let's go ahead and do the same thing here where we isolate z. So z squared is going to equal 9 minus y squared. So then z will equal plus or minus the square root of 9 minus y squared. So if I go ahead and sketch out the region that's being described here, the rectangle with its specific vertices here, just in the xy coordinate plane, we have 0, 0, one of the vertices. We have one at 4, 0, one at 0, 2, and then one at 4, 2. So this is basically the region D that's being described here. Now realize that in this region we can say the x values range from 0 to 4. So we can say goes from 0 to 4, and the y values basically range from 0 to 2. Now if I were to draw this rectangle out in a three-dimensional coordinate system, let's just say we have x, y, and z axis here, the rectangle will look something like this, where it's going to be flat on the xy plane. Now realize that z equals plus or minus the square root of 9 minus y squared, but we're only looking for the part of the cylinder that lies above the rectangle. Now if it's above the rectangle, it's basically going to be on the positive z-axis. So here's going to be positive. If you go down below, that's going to be the negative z-axis, but we only want the positive z-axis. So we're going to cancel out that negative, and we're only going to take z equals the square root of 9 minus y squared. That's only what we need since z has to be positive. So now if I were to write the formula for the surface area, it's going to equal the double integral. Now same thing, let's go ahead and just put the x bounds first on the inside integral. So we're basically going from 0 to 4, and the y bounds will go from 0 to 2 of the square root of 1 plus, now f sub x. So we need to find the partial derivative of the function with respect to x. Now realize I can also rewrite it as the partial derivative of the function z with respect to x. Since in this case there is no x variable, the derivative or the partial derivative will just be 0. And so if we were to find the partial derivative of z with respect to y this time, there is a y variable on the inside. So if I rewrite this as 9 minus y squared to the 1/2 power, I can go ahead and use the power rule to find the partial derivative. The partial derivative is going to be 1/2. We bring the power down, we keep the inside function the same, subtract the power by 1, and then multiply by the derivative, or the partial derivative of the inside function, which is just negative 2y. The 2's will cancel. Negative y is going to be on the numerator, and then the exponent we can move to the denominator. So we'll get 9 minus y squared, or the square root of 9 minus y squared. So the partial derivative of z with respect to x once again is 0. 0 squared is 0. We have 1 plus 0 plus the partial derivative of z with respect to y, which we found to be negative y over square root of 9 minus y squared. Now if we square that, we will get y squared over 9 minus y squared. Since the x bounds are put first, we go ahead and put dx, and then we have dy on the outside. Now if I go ahead and just simplify what's only inside the radical here, we have 1 plus y squared over 9 minus y squared. So I'll actually go ahead and combine these two fractions, or these two terms together, to create one whole fraction. So I'll make 1 equal to, so I will change 1 to just be 9 minus y squared over 9 minus y squared. Now that we have common denominators, I can go ahead and add the numerators. So negative y squared plus y squared will cancel, so we're left with 9 over 9 minus y squared. Now realize that we do have a radical on the outside, so if we take the square root of the entire thing, square root of 9 is 3, so we have 3 on the top, and the square root of 9 minus y squared on the denominator. So rewriting the double integral, we have the double integral, outer one from 0 to 2, inner one from 0 to 4, of what we have simplified to, 3 over the square root of 9 minus y squared dx dy. Now rewriting the inside integral, we have the integral from 0 to 4 of 3 over the square root of 9 minus y squared dx. Now we're integrating with respect to x, so this entire thing is a constant, and so the integral is just going to be 3 over the square root of 9 minus y squared times x. Let's go ahead and evaluate that from 0 to 4. We plug in 4 for x, we'll get 3 over square root of 9 minus y squared times, once again I plug in 4 for x, we get 4, minus when I plug in 0 for x, we get 0. 4 minus 0 is 4, 4 times 3 is 12, so we're left with 12 over the square root of 9 minus y squared. Now let's go ahead and evaluate the outer integral, from this time from 0 to 2 with respect to y. Now notice we have a square root on the denominator, and it is in the form the square root of a squared minus y squared. Now if it's in this form, we can use what's known as trig substitution. So we have to make the substitution where y equals a times sine of theta. Now if a squared equals 9, then a is just going to be the square root, or a is going to be 3. So we can make the substitution that y equals 3 times sine of theta. Now if we find y, we also need to find what dy is. So if you derive y with respect to theta, derivative of 3 sine theta is just 3 cosine theta d theta. So now we can go ahead and actually substitute it in. So we get 12 over the square root of 9 minus y squared. So 3 sine theta squared, which is 9 sine squared theta. Now if I go ahead and factor out a 9, I'll just go ahead and simplify the denominator right now. We'll get 9 times 1 minus sine squared theta. Now 1 minus sine squared is cosine squared, so we're left with 9 cosine squared theta. Realize we do have a radical on the outside, so we take the square root of that. It's just going to be 3 cosine theta. We do have a 12 on the numerator, so we have 12 over 3 cosine theta, and that's what's left, times dy, as shown up here. So dy, once again, is equal to 3 cosine theta d theta. So if I go ahead and erase dy, replace that with 3 cosine theta d theta, realize that the 3 cosines will cancel, so we're just left with 12 d theta, or the integral from 0 to 2 of 12 d theta. Now 12 is just a constant, so the integral with respect to theta is just 12 theta. Now before I evaluate with using y bounds, remember we substituted in theta for y, so now we need to substitute back into y variables. So earlier we said that y equals 3 sine theta. So we can say that y over 3, if you divide over the 3, equals sine of theta, so that theta is going to equal arc sine or inverse sine of y over 3. So we can make that substitution back. So replace theta with arc sine of y over 3. So I can say 12 times inverse sine of y over 3. And now we can go ahead and evaluate it with the y bounds of 0 to 2. So then we'll get 12 times inverse sine of 2 over 3, when I plug in 2 for y, minus inverse sine of, when I plug in 0 for y, we'll get 0. Now inverse sine of 0 is 0, so that will cancel, and so our final answer is going to be 12 times inverse sine of 2/3. So for number 3 now, let's go ahead and find the surface area for the part of the surface z equals xy that lies within the cylinder x squared plus y squared equals 1. So let's go ahead and start off by finding the partial derivative of the function z with respect to x. So in this case, x is the variable, y is a constant. So the partial derivative of x times y is just going to be y. And so now the partial derivative of z with respect to y this time is just going to be x. So if I go ahead and write out the formula for the surface area, it's going to equal the double integral of the square root of 1 plus the partial derivative of z with respect to x squared, which is y squared, and then plus the partial derivative of z with respect to y squared, so then x squared. So now let's go ahead and find our bounds of integration. Now the part of the surface lies within the cylinder x squared plus y squared equals 1. Now remember, when looking at the equation of a cylinder, whatever variable is missing here is going to be the axis of the cylinder. Since the z variable is missing, that cylinder is going to be on the z-axis, and this value is just r squared, or the radius squared, so r will just be 1, or the radius will be 1. So if I were to draw this cylinder out in a three-dimensional coordinate plane, it will look something like this. We have the cylinder, and the radius of the cylinder is going to be 1. Now let's say we're above the z-axis and we're trying to look exactly down on the z-axis. So what we'll get here, or what we'll be looking at, is basically the base of the cylinder in an xy coordinate plane. The radius is obviously still going to be equal to 1. So this is basically the region that we'll be looking at in order to find the bounds of integration. Now a couple videos ago we learned about how to use polar coordinates to evaluate double integrals, and so especially when dealing with circles, like in this example, it is very beneficial to use polar coordinates instead of just rectangular coordinates. Even though you can use rectangular coordinates, it's going to be much more difficult. Now realize that in polar coordinates, instead of x and y as our variables, we have r and theta. So let's go ahead and find the bounds in terms of r and theta. Now realize that r just goes, or the radius just goes from 0 to 1. So we can say that r is between 0 and 1. And then for theta, obviously it's a full circle, so it starts at 0 radians and goes all the way to 2 pi radians. So we can say that theta ranges from 0 to 2 pi. So if I go ahead and rewrite the integral now, we get the double integral. Now remember, the r bounds are always going to be on the inside integral. So from 0 to 1, that's going to be the r bounds. The theta bounds are from 0 to 2 pi. Now we need to go ahead and change this into polar coordinates. Now realize that x squared plus y squared equals r squared. So we can simply just change it into the square root of 1 plus r squared. And don't forget, whenever we use double integrals in polar coordinates, we always have to multiply by that extra r variable. And then so we have dr and then d theta. Now if I go ahead and evaluate this, I'll rewrite the inside integral from 0 to 1 of r times the square root of 1 plus r squared. Now we're going to integrate with respect to r, and so this is just a simple u substitution problem. So I'm going to set u equal to 1 plus r squared, then du is going to equal 2r dr, so then dr, if I isolate it, will be equal to du over 2r. If I go ahead and substitute that back into the integral from 0 to 1 of r times the square root of u, because I replaced 1 plus r squared with u, times dr, which is equal to du over 2r. Realize the r's will cancel. The 1/2 can come outside the integral as a constant. We get 1/2 times the integral from 0 to 1 of, I'll rewrite square root of u as u to the 1/2 du. Now the integral of u to the 1/2 is just going to be 2/3 u to the 3/2. Don't forget, we do have a 1/2 outside as a constant, so I'll multiply by 1/2. 1/2 times 2/3 is going to be 2/6 or 1/3. So we get 1/3. Now I can go ahead and substitute back in u, which is 1 plus r squared. So 1/3 times u, or 1/3 times 1 plus r squared to the 3/2. So if I go ahead and rewrite that down here, 1/3 times 1 plus r squared to the 3/2 power. Let's go ahead and now evaluate that from the bounds of 0 to 1, from the r bounds. So if I plug in 1 for r, we'll get 1/3 times 1 plus 1 squared is 2, so then 2 to the 3/2 will be the square root of 8, minus, when I plug in 0, we'll just get 1 plus 0, which is 1, 1 to the 3/2 is 1. So now we can go ahead and integrate the outside here from 0 to 2 pi, and then with respect to theta this time. Since this entire thing is a constant, the integral is just, I'll rewrite it as the square root of 8 minus 1 all over 3 times theta. And so now we can go ahead and evaluate that one from the theta bounds of 0 to 2 pi. Now if I rewrite the constant outside, so square root of 8 minus 1 over 3, now I can go ahead and plug in 2 pi for theta. We'll get 2 pi minus, when I plug in 0 for theta, which gets 0. And so we're left with 2 pi over 3 times the square root of 8, which I can simplify to 2 times the square root of 2 minus 1. And that is going to be the final answer for the surface area.